This video final result can be downloaded by following the link in the description. I will be crystal clear. It is not possible to obtain a good non-photorealistic result in a real engine. Because of its structure and rendering pipeline, every attempt in that direction inevitably translates to a collection of workarounds that pile up onto each other, inexorably leading to complete chaos. That said, let's see how to obtain a cel shading in a real engine, like a proper one, without breaking any physically based lighting rules. But before doing that, let's have a quick look at how it's usually taught in basically every other tutorial on YouTube, and why that approach does not work. Since a real engine follows a deferred rendering pipeline, the only place that makes sense to manipulate lighting data in is the post-process stage. I agree on that with everyone else, and that's also the first reason why this engine is not well suited for this kind of job by default. Basically, at the post-process stage, all the rendering has already happened, including the lighting calculations, so we have no way of individually controlling how each source of light is applied to the surfaces, for example. We're forced to deal with the complete final result as one single entity, and that already restrains a lot the amount of things we can do, but to be fair, we can still do many things. So, let's create a new material, let's assign it to an unbound post-process volume, let's set it as a post-process material, and let's make it run before the toon mapper. Or during scene color after DOF, apparently, if you switch to 5.4. Now we can start. Let's take a scene texture node and let's set it to post-process input 0. This is needed to display the rendered image. And now let's start following the most common steps done by most of the other tutorials. Let's duplicate the scene texture node and this time let's set it to diffuse color. Let's desaturate both of them and let's divide the post-process input 0 by the diffuse. This operation, they tend to say, returns the brightness value of the scene. What I can tell you is that at this point you already compromised the image and from now on it will become a matter of adding patches to work around problems. But let's keep going forward. What's done from now on starts to diverge between tutorials as it starts to come into play what the specific person wants to achieve. But more or less we could say that it's always some form of this. We add an if node to the graph and we define a brightness threshold that we'll use to either pass through the diffuse color as it is or a darker version of it. And that returns a very good cel shading feeling image. And if we want more bands, we can concatenate more ifs, each with a different threshold and a different multiplier for the diffuse pass. There you go, here is cel shading in a real. But let's give it a closer look. The sky is black. Well, sadly this will be a problem with every approach we take, as its data is not included in the G-buffers used by the rest of the scene. The most common way to fix it that I've seen is to create a mask based on depth to put back there the original image sky. Metals are black. This is because the diffuse pass does not contain their color information, as it has internally been moved from base color to specular. This step has been now made explicit by Substrate, Epic's new material pipeline. I have a video that goes through this stuff, maybe you want to give it a look. Anyways, this problem can be avoided by simply replacing the diffuse pass with the base color one. Lights lose their color. That's because we're desaturating our passes at the very beginning, hence removing the color information, which we'll introduce afterwards through the base color pass, which knows nothing about lights. The only tutorial I happen to find that tried to solve this issue is Prismatica Dev's one. His solution is to desaturate again the image, to then multiply it by the normalized post-process input 0 pass. What he says about that is that the normalization returns pure color without any brightness variance, so it can be used to reintroduce all the correct colors into the cel shaded image that, after the desaturation, only contains brightness information. Well, kinda. Explaining this thing properly would require a whole dedicated video, but I can give you a little overview. This normalization is almost the correct operation needed to obtain the pure color information, aka the hue of the color. The problem is that the normalization sets the length of a vector to 1, confining its values on the surface of a unit sphere. In case of colors, which can only be positive, we are confining them on an eighth of a sphere. And if you imagine the three axes to be the RGB color components, you can see that we're not covering the full spectrum. It is possible to obtain the primary colors, but not all the other ones, not even pure white, which comes out as a light gray. The RGB color space is actually cubic, not spherical, so pure colors lie on a unit cube faces. The correct operation, in this case, is to find the maximum RGB color component and use that to divide the color. Moreover, there's another error. Can you see how the processed image is still darker than the original one? This will throw off all your exposure, light and texture values and make them susceptible to changes to the post-process. Dangerous. The culprit of this is this desaturation. It's used, like at the beginning, to calculate the brightness of the image. Once again, this is not quite the correct operation to do. The desaturation doesn't return the true brightness of a color. It weights differently the RGB components to return something as close as possible to the human eye's perceived brightness. And that's why the green is considered the most bright, followed by red, and blue is the darkest one, because our eyes are sensible to those wavelengths of light in that way, more or less. And by artificially making some colors darker or lighter, the black and white result is better perceived as matching its colored counterpart. But in this case, we need to be mathematically accurate. If we consider the case in which we only have pure colors, we should get the brightness value of 1 for all of them, regardless of the hue. Once again, finding the highest component among R, G and B is the solution. Then, why did the saturations at the beginning work? They do just for a lucky coincidence. The two errors caused by the two desaturations nullify each other in the division that comes afterwards. Let's swap them anyways with the max of the components, as it spares few instructions too. Hard-coded thresholds will jeopardize the flexibility of your lighting. If you make the environment brighter or darker, your thresholds will move back and forth and won't be valid anymore. So either you add a ton of them, or you find a way to organically move them along with the intensity of your lights. I could carry on, but hopefully by now you understood that this approach is full of fallacies. Even after fixing some issues, there are always more behind the corner, and trying to work around all of them would result in a huge endeavor of growing complexity as the patches start to pile up. So, let's leave only the properly working parts and let's try a better approach. For how I see it, if we want to make a cel shader in Unreal without diving into its source code and basically rewriting all of it, there is one hard constraint that we're not allowed to break. Our work must stick to the physically based rules. So, the first step will, of course, be properly setting up lights and tone mapper. I'll briefly explain the motivations behind the setup I'll walk you through, but I won't repeat myself on why and how things work better in that way. If you're interested in the topic, in my channel you can find a series of videos specifically dedicated to lighting in video games, in which every concept is exposed by someone that knows way more than I do about this stuff. In fact, a big part of what you'll see me doing in this video is an application of the new knowledge I gained by working on those videos. So, let's start from the sun, 120,000 lux, and source angle at 0, since for our cel shader we want our shadows to be super sharp. Let's now go to the post-process volume and let's go with order. Let's remove the bloom to have a cleaner image. We can use it, of course, and to be honest, if I had to use it, I would use the convolution, given its clear superiority, but to be honest, it's just a disturbing element at visual development stage, so off it goes. Let's set the correct exposure for a daytime with a clear sky, like the one we have now. No lens flares, no vignette, since, like the bloom, they only dirt our image for now. Let's reduce to a minimum the blue correction so that the blue tones pass through with proper vibrancy. Yeah, at the moment it's quite subtle, but later it will become more evident. I'll point again at that so you can see better what I mean. Now the most important part, setting up the tone mapper. If you follow the videos on lighting, you'll recognize the values I'm about to set. Slope at 0.7, tone at 0.3, white clip at 0. The aim is to obtain a dull, low contrast, low saturation image. This is normally a friction point in a production context, as people that don't know how images work just see a boring outcome, and they start to complain, add bugs on Jira, assign new tasks to make a better image, and panic spreads among producers and managers. While who knows about photography, cinema and video making finally realizes that even in video games we can work professionally on images. What you're seeing now is the equivalent of a raw shot with a properly set professional camera. It looks like that because we're compressing in the captured image as much data as possible in order to maximize the freedom we have in post-production. I can give you an immediate example of this. Let's go to the color grading tab under global and let's set the contrast to 1.25 and the saturation to 2. And now our colors become as we would have expected. Moreover, it's now also possible to observe better the effect of the blue correction. You know what? Greens are coming across a bit too extreme. Let's reduce their saturation. Alright, let's continue on the list of parameters in the post-process volume and we reach lumen. Now we have a choice to make. Remove all GI and reflections altogether or keep them and fight against performance issues and artifacts. The result you can get without them is very good, to be honest. You have more separation between colors and shapes, and for a toon image I think it works very well. On the other hand, with lumen, everything will look more organically integrated in the scene. Keep in mind though that you'll likely need to use higher quality settings than usual, to suppress as much as possible its artifacts, which will become very apparent and annoying thanks to the quantization of light made by the cel shading. So, your choice. In this tutorial I'll keep lumen on because it will give me a clearer way to later show off a thing that I'll do in the shader. But other than that, if you disable it, you'll still be totally able to follow this video in its entirety. So, as I said, let me raise lumen's quality settings. The only thing I'll set to a minimum is the update speed, as it will make the cel shading bands derived from the GI luminosity wobble less. And we're done with the post-process volume setup. Just in case you decided to disable lumen, it's worth mentioning that this enables the screen space ambient occlusion. It can be useful to tune it up to give some more volume to the scene, or you can disable also that to reach an even flatter look. Oof, are we finally ready to dive into the shader? Not yet. As you'll surely know by now, perfectly setting up the lights of a scene without also following up with a proper material pipeline for the props leads to disaster anyways. So, let's have a quick overview of the self-imposed rules I've come up with in this project to have consistent results that work well with the tone mapper and post-process. They are a bit different and more restrictive than the usual PBR guidelines, I may say. For all these test meshes, I'm using this single test material that I've set up with a bunch of parameters for base color, specular, roughness and metallic. All of them are set as custom primitive data, so I'm able to change them on individual meshes instead of creating a ton of material instances. The, let's say, default setup for a material that works well with a cel-shaded look is specular at 0, roughness at 1 and metallic at 0, so it becomes pure diffusion and it's shaded only based on light direction, without any reflection or a highlight that moves relatively to the camera. One hard constraint that I've imposed to the assets in this scene is that their base color saturation must be capped at 0.5. This is, yes, to ensure a better raw-looking image out of the tone mapper, but mainly because I saw that, with values lower than that, we start to lose pieces of indirect light contribution. Look at this red Gimli, for example. If I saturate it more than that, I completely lose the bluish contribution coming from the skylight, resulting in a more boring result. And, more than anything else, it wouldn't be consistent across the scene, as other objects with less saturated colors will still get it, creating a visual disparity between high and low saturated props. Moreover, a saturation of 1 introduces some zero values in the base color buffer, that, as we'll see later, always brings some problems. Aside from that, the electrics and metals can be set up as usual. Let's finally go to the node graph and work on this so-called cel shader. And hear me out now, as what I'm about to say is the foundation on which all the subsequent work will be based upon. As we already said, if our post-process material runs before the toon mapper, the image we work with is the raw render of the engine, in HDR. This means that colors haven't been remapped to a range that can be displayed on the screen yet, but they still contain literally the luminosity values of the scene, which will be physically correct if we set up our lights properly. And, as we saw earlier, we can grab the brightness of the image by calculating the max value of its RGB component. Now, I want to show you a thing, but to do it I need a way to print the pixel values on the screen. To do that, I divide the screen in a grid and I sample only the pixel at the center of each cell. In this way, I create nice and wide areas with constant values that I can pass to the function debugScalarValues to overlay the printed value of each cell. Now we can clearly see what kind of values we're dealing with, and we can finally understand why it is so difficult to keep a cel shader in check with precision and identify good thresholds to use to quantize the light. These values have an incredibly extended range. We're going from 100 units to 35k, and they clearly change in a non-linear way. Well, in reality these values, by being physically accurate, follow a very precise exponential rule. Let's say I have a cell of brightness 100, for example. If I want a second one that is twice as bright, I'll give it a value of 200. Now, if I want a third one that has the same perceived brightness difference of the second from the first but from the second one, I don't give it a value of 300, but I have to double the value again, so 400, and so on. So let's now say that our base luminosity value is 2. If we elevate it to a power, we can double or halve any given value by simply increasing or decreasing the exponent by 1, and that gives us an exponential behavior. Okay, that's interesting. So let's assume that these values we see in the scene are actually powers of 2. If we do the inverse operation, we should be able to calculate which their exponent is. So, if the inverse of the addition is the subtraction, the inverse of the multiplication is the division, the inverse of power is... What? No, it's the logarithm. And since it's the inverse of a power of 2, we need a logarithm of base 2. By adding this operation and printing the result, we immediately see that everything makes more sense, all of a sudden. Numbers are in a more reasonable range and they actually change in a linear fashion. And oh my, look at that! The number in each cell matches exactly the EV needed to correctly expose that specific area. This is very interesting. Then I may ask, what if we quantize these exposure values to generate the cel shading color bands? Let's round them and let's reconvert them in luminosity intensity by using them as an exponent of a power of 2. And let's also remove the grid subdivision of the image and the printed values. And there our cel shading bands are. Now we can add the color back to our image. The important thing to point out here is that our post-process is not changing at all the brightness of the scene. It's just breaking up the luminosity gradient in discrete steps, avoiding the need of any lighting and texturing workflow change from the standard one. Moreover, if we want control on the amount of bands we have, we can sandwich the rounding of the values between a multiplication and a division for the same number. Alright, we're finally ready to start working on a proper cel shader. Let's remove everything and let's start from scratch for the last time. As we did before, let's remove the base color from the image by using it as a divisor. To be sure to not create any numerical error, let's ensure that we are not dividing by 0 with a max node. The sky, for example, has always a value of 0 in the base color buffer. Now we have pure light information, including its color, not just the brightness. Let's break it up into its components, but in a slightly different way than usual. Let's convert it from RGB to HSV, hue, saturation, and value. The V component is called like that just because of Epic's choice, but it's the same as saying brightness or luminosity. In fact, the acronym for this color space is also HSL or HSB, they're all the same. Before starting to mess with things, let's first add all the inverse operations to recompose the final image, so we don't work blindly and we can also double check that all we're doing is working as intended. Let's put the HSV components together, let's reconvert them to RGB and let's multiply the result by the base color. If we've done everything right, we should see the same image that the post-process input 0 outputs, aside from the black sky, which we'll bother to fix later. Good, now we can proceed and replicate what we did earlier to quantize the luminosity of the scene. And here is our cel shader again. Let's make it even prettier though, and flexible. With the rounding operation, every pixel can only be either of one value or another. It's always better to have a little area of transition values between one step and another. To achieve so, we must develop a function that has the shape of a smooth step. I won't go into details of how I derived this, but it's basically made of two mirrored exponential curves and it works only in 0-1 range. This is how it's implemented in Unreal, nicely packaged into a material function that you will of course find inside the sample project you can download by following the link in the description. You can see it as an enhanced smooth step. Anyways, in our case we want to use it to replace the rounding. But since the function works only with 0-1 ranged values, we have to first decompose our EV values in their integer and fractional part. Now we can apply the curve to the fractional part and re-add it on the integer one. And now we can freely choose how much we want to compress our gradient, and even if we end up using the maximum contrast, we'll always have a tiny bit of smoothing sticking around to help us. If we just needed to work on the brightness component, we wouldn't have needed a full HSV conversion. Why don't we try to quantize the hue too? Just a little disclaimer, from now on we go a bit more into the domain of my personal choices and taste. At this point you have already successfully cel shaded the image, but that's not enough to create a strong and unique stylization. So I'll walk you through some of the manipulations that I will do to push the image further. My idea, in this case, is to reduce the amount of possible colors that the lighting can have, and since the hue is a number in 0-1 range, we necessarily need to identify a multiplier for the number of hues we want to retain. In this case, I want to restrain it to only display primary, secondary and tertiary colors, so 12 hues. In this case though, I won't use the maximum contrast as I find it visually annoying. I'll keep a bit of blur between the bands. Let's put the sky back to where it belongs, by creating a mask starting from the base color and checking where it has the value of 0. Then let's use it to put back the original sky in the final image, without any cel shading done on it, as I personally find a quantized sky awful. Now I'll tell you what. Very nice the usual cel shader with clean and flat bands, but I'd like to reintroduce some volume to the scene. And to do that I'll blend back in just a tiny bit of the original brightness values. I also think that metals have way too many value steps, I don't like it. We are almost losing the cel shading effect. So let's grab the metallic pass and let's use it as a mask to reintroduce a lower amount of EV bands only for the metallic surfaces. You know what? Let's keep working on those metals and let's give them some more life. The technique I'm about to show you, it's a trick that I've developed in the past while working on a prototype for a stylized game, while trying to replicate some painting tricks used by some very good concept artists I was working with. It consists in adding a fake rim reflection around the object. Light if the geometry is looking upwards, darker if it's looking downwards. Adding fake lights is always a very dangerous thing to do though, but thanks to this approach we developed, we can do it in a very smart way. But first, let's create the gradient for it. Let's calculate the dot product between the camera vector and the world normals. This is the base to obtain a Fresnel. Now, I'll add an operation that is not strictly necessary, but that I personally find very helpful to better control these kind of values when I want to remap them, like in this case. The dot product between two unit vectors returns the cosine of the angle between the two, and the cosine is a curve. This means that when you look for precise thresholds, you have to deal with an uneven distribution of values, making the task a bit harder. If, instead, we first calculate the arc cosine of this value, we obtain directly the angle, in radians, between the two vectors, which has a linear behavior. Let's convert the radians into 0-1 range by dividing by half pi, and let's now look for the thresholds we like. As final touch, let's square the final gradient to give it a more natural look. This is our mask, the area of the image that will be affected by our fake reflections. The values we'll be modifying the EVs with are simply the B component of the world normals, after scaling them as we like, which means by 2 in this case, as I like the result. You'll see that in a moment. Let's multiply them with the Fresnel mask and the metallic bus to obtain our final values. This is what we created, with positive values colored in red and negative values colored in blue. Now, as I anticipated, thanks to our setup, we can handle this faked light in a very interesting way. We added a CV values variation right after completing our quantization of the luminosity of the scene, as in this case I don't want it to affect the cel shading color bands. What we just did in practice is to raise by 2 exposures the upper silhouette of metallic surfaces, while lowering by the same amount the lower one, making it self-balanced over the image as a whole. It works in every light condition and doesn't make the stylized image diverge from the original, physically based one. Another superpower we unlocked now that we know how to calculate EV values directly inside the shaders is that we can also calculate the camera exposure directly from here. We just need to take the pre-exposure value and calculate the base 2 logarithm of its inverse. That's so easy that it took me only years of experience, a lot of random events happening lately, and the stars aligning for me to discover. I could have used this incredibly useful information so many times before, but I guess it was still faster than waiting for Epic to write documentation that actually explains to you what the nodes are for and how they're supposed to be used. In this case, it's useful to do a very peculiar thing. Since the exposure value of the camera tells us which luminosity value of the scene is considered as middle, we can use it as a guide to understand where are the shadows and where are the highlights. So we can subtract the camera EV from the scene EVs and saturate to create a mask that tells us where the shadows are. And now, for example, we could use this information to interpolate between 2 colors that we then multiply by the scene brightness. The result is a bichromatic version of our scene that we can use to give a strong chromatic stylization to the original. This is probably the most dangerous thing we did so far, as it may require some specific adjustments based on cases, but I think it's still in the manageable field. It's also important to keep in mind that we can add color stylization in the classic way, through the color grading in the post-process volume, but in this way we can probably go more extreme. Now that you saw it, I'll disable this feature though, for the sake of keeping the image clean. Alright, I'd say there's only one very important element clearly missing from our stylized image, right? Where are the outlines? Likely on this I've got almost nothing to explain, as to this date I've already done 2 videos on this very topic, the outcome of which you can download by following the link in the description of these or those videos. So I'll just include one of the outline filters I've already done and maybe add some little improvements. Alright, let's add the circular Laplacian filter version and add some thresholds to the output data to obtain our outlines. Now we can multiply them on top of our cel shaded image and merge everything into one. That's it. Well, more or less. The lines can become quite dense and annoying at distance. It will be better to gradually remove them as they get further away from the camera. This thing can be done in several ways, but today I'll just show 2 of them, a very easy and straightforward approach and a more elaborate one. The first one consists in taking the scene depth, define the range in which we want the lines to fade, and use it to interpolate to a value of 1 the outline pass before merging it into the final image. It does the job, but yeah, not with the best looking outcome. I don't like how many edges become a bit transparent. I'd like something better. What if we progressively reduce the kernel size directly? In that way, instead of making the lines progressively more transparent, we would actually make them thinner, which makes more sense too. Alright, it can be done, but it requires a little mod to the code. Let's expose the kernel size as an input for the custom node, and let's use it as a replacement of the direct value set we had before, while also adding a floor to ensure that we only deal with integer numbers. All of this now implies that we're not tied to the use of a single constant value for our kernel size, but we can input a gradient too. Let's grab the fading gradient we did before and let's remap it to desired kernel sizes before passing it as an input. Okay, it's working, but there is a very evident problem where the outlines are supposed to reach the minimum thickness. And it makes sense if you think about it, as with a size of 1, the kernel has no neighbor values to compare against, and it reads itself as an outline. So maybe we can add a little exceptions that returns no outlines if the kernel size is lower than 2. And the issue is fixed. And look at this solution works definitely better than the previous one, while probably sparing some GPU cycles in most cases. Cool, we have our outlines and our stylization is perfect. Pretty average if you ask me. I mean, they clearly do the job, but we're developing our unique artistic style that is better than everyone else's, right? So we must think a bit more outside the box. So let's try to reinterpret this element under the same light of this physically based stylization, the exposure values. What we care the most about is to stylize the image while keeping its overall brightness unchanged. By adding an amount of black lines that is not really controllable, we end up darkening the final result by an unknown and shot-dependent amount. But we still want to add to the shapes that sweet pop the outlines give us. How can we do it? What if we use the filter output as further EV offset? That might work. So, the value the filter returns can be both positive or negative. If the outline is detected outside of a shape, they're positive, if inside, negative. And this is valid for the part based on depth. For the normals, I'll do a slightly different thing that hopefully returns me a similar result. I'll dot product it with the camera vector, which seems to return something kinda analogous. Now, before joining them together, let's visualize again the data coming out from the depth. Probably you already noticed it earlier. The filter is a bit too sensitive and it reads as outlines the edges of the mesh triangles too. Even if they are quite light compared to the correct ones, we should filter out that stuff. The fact that they are detected as light outlines actually gives us a clean way to get rid of them. If we imagine the outline values as an actual inclined line in a graph, where the higher above 0 you go, the harder the positive edge, and the lower the harder the negative edge, we understand that the problematic area should be right around the area close to 0. So we should try to compress the line until only the values that identify a sure edge remain. To do that, we separate the sign from the absolute value. Now we can subtract a threshold from the latter, clamp all the negative values out, and then reapply the sign. The higher the threshold, the more outlines will be filtered out, so we need to find the right value that only removes what we don't want, without sacrificing too much the rest. One thing that you can notice here is that high poly meshes are easier to deal with, while lower poly need a more aggressive approach. Now we can simply add together the two outlines data. My idea is to lower the V's with the positive outlines, the ones outside the shape, and do the opposite with the other ones. For this reason, I'm going to negate the values. And last thing to do is to clamp, as edge values straight out of the filter can go crazy high. I'll use 1 for the internals and -2 for the externals, as I still want to mainly pass through the feeling of having a dark outline. And, as we did for the fake metallic reflection, let's add all of this right before reconverting the scene from EVs to actual brightness. And there you go, we obtain this effect that is a bit lighter than the usual outlines, but still makes the shape pop out a lot. We could go on indefinitely and add more and more stuff to our style, but I can say I'm satisfied with what we achieved today. And let's say that's it, we found our style. Now I can go back to the post-process volume and work on my post-production with the peace of mind of knowing that we didn't break the physically based pipeline, and everything will still work as intended. I once again thank my patrons for all their support with a discount code for the download of the sample project you can find in the link in the description. Don't forget to subscribe to the channel to not miss future videos, and maybe, if you fancy, join my Discord server. As a final note, I want to reiterate once again that what you just saw has been unlocked by the new knowledge I've acquired recently on how to properly work with physically based lighting, thanks to the video I've been doing with Eros on this very topic. I hope that this video demonstrates how not only a knowledge of your tool's capabilities, but especially knowledge of their limitations is the key to get creative and find new solutions. I hope this video gave you new hints to create your own original artworks, and if it did, I'd be happy to see work in progresses and show-offs in my Discord server. That said, I'll catch you in the next video.